Okay, AP Calculus AB, Unit 6, Day 5, lesson. So let's see, we're going to go over some of the important points. Some of these we've talked about before, more than others. And just to start to get familiar with the terminology. So CP is for critical point. Now, if I was to draw a picture of a nice, kind of smooth curve, a critical point is when the slope is 0. So you get a nice flat spot. It's a peak or valley a lot of times, but also it could be like just a kind of a more plateau. But we call those critical points. So it's when f prime of x equals 0 or undefined. So let me show you some examples of undefined. So 0 or undefined derivative. So undefined would be like a corner, sharp corner, a cusp, which, could maybe look like that. Or, this one's kind of an interesting one, a vertical tangent. Okay, so vertical tangent would be like maybe like a cube root function, kind of looks like this. And it has a tangent line straight up and down. So it's smooth. These other ones happen usually at places where the graph isn't smooth. So the derivative doesn't exist because the derivatives don't agree. But this one, the derivative is just infinite. Stationary point is like a sort of a subset of critical points. So it's, stationary you think of as not moving, right? Not moving. So sometimes we kind of use this description with like motion problems. So standing still. So it's a subset of critical points. It's specifically only when the derivative equals 0. So if you apply to like motion problems, it's like it's not moving. Zeros are just when a function equals 0. So it's when the output or the y value is 0, which is also the same place as an x-intercept on a graph. So we've been talking about zeros a lot. IP for inflection point, point at which concavity changes. So the concavity changes from up to down, down to up. It might is the key word, happen when f double prime equals 0 or undefined. Might happen there. It's not guaranteed though. Relative max is it's a high point, but not necessarily the highest. So it might not be absolute max, but it's a high point locally. A lot of times I like to refer to it as a peak, sort of like a high point, a peak. It's a relative min is a low point, but not necessarily the lowest. I like to use the term valley. It's not a very technical term. Okay. Absolute max is the highest point for sure. And it could happen at a peak. Peak could be the highest point, or it could happen at the edges at an endpoint. So you got to consider that. Absolute min is the lowest point everywhere, which could happen at a valley or an endpoint. So just some quick rundown of terminology. Okay, so here's just a place where we can try and practice identifying these just from a picture, which is probably the easiest, but and probably not the way we're going to do it in the long run. But let's see. Let's look at this kind of funny graph. And so one of the things is You see these little lines. I'll probably help you out. These are horizontal tangents. This looks like it's probably like a vertical tangent maybe. And so we're saying, okay, well, let's identify all the critical points. Well, the critical points, let's say the x coordinates. Let's say that these are like x coordinates, okay? So location. So this is going to be x equals, critical points would be B, D, F, and G. G is a critical point because the derivative is undefined. A sharp corner is going to be a critical point. Stationary points are specifically only the ones that are flat. 0, B, D, F. The zeros are where this graph intersects the x-axis, A and H. Inflection points, well, I would say inflection point there changes, here goes from up to up. G could be inflection point at a cusp if it changed the concavity. It doesn't this time. So inflection points are at C, E, and F. Relative max are just the peaks, B and G. G is a relative max. Relative min would be D. That's it, just D. Absolute max is at G. Absolute min is actually at A and H. It's a tie. This is the lowest points of the whole graph, right? So the absolute min did not happen at a valley. I want you guys to go ahead and practice, try to answer the same questions for this graph. So go ahead and just finish this right here. Try these, pause the video, see if you can identify them all. Okay, your next test is going to have a bunch of points for this kind of stuff, and it's quick and easy, but people lose a lot of points on it. They forget ones, they miss ones, whatever. So try number 2, try and identify critical points, stationary points, zeros, inflection points, relative max, relative min, absolute max, absolute min. Okay, so try that for number 2. Pause the video, try it, and then unpause it, and you can check your answers. Okay, critical points are going to be x equals B, C, E, H, G, and H. So all of those are critical points because the slope is either flat. Oh, F. F is critical point. That one could slip through because it's a vertical tangent or a cusp or a corner. So B, C, E, F, G, H. Those are all critical points. Stationary points are only the ones that have the flat zero slope. So that's going to be C, E, and G. Just C, E, and G. Zeros are the x-intercepts. So there's one of them at I. Inflection points, that goes from concave down to up. So D is 1, H is 1, or F is 1, G is 1. This one goes from up to down. So H is an inflection point. That's one that'll get by people. So we're going to say D, F, G, and H are all inflection points. Relative maxes are the peaks. So there's a peak at C and H. Relative mins are the valleys. There's a valley at B and E. Absolute max is the highest point, which is at H. Absolute min this time happens at the edge at I. So now I'm going to wait to fill these out. We're going to go to the other side and go over some more definitions first. And then we'll come back and look and see if we can fill it out based off these definitions. So on the back of the page, let's talk about what increasing, decreasing, concave up, and concave down mean and how to identify them. From a picture, or even, we'll start with the picture. So increasing just means you're going uphill, left to right, right? So this is left to right. Generally, when you look at graphs, you think of them as left to right. So it's just uphill. Decreasing is downhill, left to right. Concave up, it kind of curves up. Concave down, curves down. So we're going to add some stuff here in a second, but let's go back and look at the front and see if we can identify this. So for the first one, Where is it increasing? These are generally intervals. Okay, so these are intervals. The last ones were points. Okay, so these are intervals. These are chunks of the graph. So where is it increasing? We'd say so increasing, we're going to say it's increasing on this first graph. We'll do this one together from A to B. And then B to F and F to G. But then should we include the edges or not? So that's kind of a big question. Should these be open or closed intervals? Open or closed dots? So should it be A to B parentheses or should it be A to B brackets? Okay. Now, so is it increasing at the top of the peak still or at the bottom? Or, is it increasing at A and B? Like, is it still increasing? So here's the deal. I think my gut feeling is, it's not increasing, it's at the top, because if it's increasing at the top, then you're also going to include it for decreasing. So it's increasing and decreasing at the same time. But some people say to include it. In fact, our book includes it. The AP test includes it. So for increasing, decreasing, we're going to include the endpoints unless there's a reason not to. Okay, so this is our book. The AP test includes the endpoints, whether you like it or not. Okay, so we're going to do A to B, and then you would do B to F, but then you would also include F to G. And so since F is including both of them, we really should go say B all the way to G. B all the way to G. Do not split it up. Okay, don't split it up. And I think in this case, even though the slope is 0 at F, it is higher than the point directly to the left of it, and it's still lower than the point directly to the right of it. So, I mean, I totally get why we would include F for both of these, but the endpoints, we include the endpoints for increasing, decreasing. That's just the stance that the AP test takes in our textbook. So it's good that so that's the stance I'm going to take. F is decreasing. So F is decreasing from B to D, it's going down, and we include the endpoints. And then also G to H, it's decreasing. So those are the two intervals. Concave up, so you might emphasize, draw the, kind of the concavity. So it's concave up from C to E, and then from F to G. These we do not include the endpoints. We never include the endpoints for concavity. So C to E, F to G, and then also G to H is concave up, concave up, concave up. Concave down would be A to C, and then E to F. Okay. So we just got to get used to this and understand what to look for. I mean, and honestly, we're kind of being, it's easy right now because we just look at pictures. In the future, we're not going to have a graph. We're going to have to figure this stuff out without a graph, which I'll show you guys how to do next. Why don't you guys try example two and identify the increasing, decreasing, concave up, and concave down intervals for number 2. So go ahead, pause the video, and then try it out, and then unpause it, check your answers. So I'm going to assume now that you've tried it. And so increasing is going to be B to C, brackets, and then E to F to G to H. So E all the way to H. Don't break it up. Decreasing is going to be A to B, brackets, and then it's going down again from C to E, and then it's going down again from H to I. And then concave up would be D to F, and G to H. Concave up. And then concave down, down, down. Now you got to break it up at B. So it's going to be A to B, and then also B to D. Don't stop at a peak. It goes concave down all the way to D. But you do have, even though it's concave down in both of these, you got to break it at B because there is no concavity at B. And we don't include the endpoints. So then concave down would be F to G, and then also H to I. So that's all the concave down intervals. So that's part of it. You're going to have problems like this on your next test where you have to just look at the graph and tell me which ones are which. It's fast. There's not no work to show. But you got to make sure you know what you're talking about, what you're looking for. But usually we're going to have to use algebra and not have pictures of the graph. So how do we identify? And we already kind of wrote some of the algebra for critical points. F prime is 0 undefined. We're going to do line checks for relative maxes and mins and inflection points. We're going to do extreme value theorem for absolute maxes and mins. Increasing, decreasing, though, we haven't done that much. So to identify it, it's where the derivative is positive. Where the slope is positive, the graph is going up, right? And where the slope is negative, the graph is going down. And so we're going to use line checks to help us find that. So we're going to find this, we're going to figure out where equals 0 undefined and then do line checks and do plus minus, figure out where it is. And then for concavity, it's specifically where f prime of x is increasing, which translates into f double prime being positive. So that's why we use the second derivative to identify concavity, is because it's the derivative of the derivative. It's whether the first derivative is increasing or decreasing. And so here f prime of x is decreasing would be concave down, which is where the second derivative is negative. Now I want to help this make sense for you. So we're going to draw a picture. So here we'll draw a generic concave up curve. And if you were to just put some of the slopes here, you'd say, okay, I mean, first of all, for sure, concave up. This is concave up, right? But I want to connect it to the derivatives and stuff like that. So if we do a couple just example slopes, like slope here is 0, slope here is 1, slope here is -1, slope here is maybe -2, slope here is -2, is +2, right? And so what's happening is if you look at this, it goes from -2 left to right, okay? It goes from -2 to -1 to 0 to 1 to 2. So the slopes aren't all positive or all negative, but they're getting bigger all the time. They're increasing. So what happens is f prime of x is increasing if it's concave up. Now, that means the derivative of the thing you're saying is increasing is positive, and so then that means that the second derivative is positive. But that's why the second derivative being positive is concave up, because that means the derivative of the first derivative of all the slopes is positive. So concave down, here's an obvious concave down sketch. And if you're to take the similar approach, just label some quick slopes on here that seem like they would be close to what's going on, right? It's going from 2 to 1 to 0 to -1 and -2. The slope is always getting smaller and smaller and smaller. So that means f prime of x is decreasing, which means the derivative of it, the second derivative, is negative. So that's why the second derivative being positive or negative affects the concavity or tells you what's going on there. So let's try a couple problems without graphs. So there's some different things. We don't need this. There's some different things that we can get from this. There's a lot of information we get from this. We could just talk about the y values of the graph, which we're not going to usually do. But we could say, well, where are the zeros of the graph, right? So we could factor it, set it equal to 0, and x equals 0, and x equals 6. Now, this is one of those bounces off the graph. And we could do a line check with the original graph. Test a point. X equals 7 is positive, negative, stays negative, which means the graph is below the x-axis. Graph is below the x-axis. The graph is above the x-axis. So these are called zeros, by the way, right? These are zeros. So, I mean, we're not going to usually do that line check. But it is something we could do, right? Do a line check. Now, what's usually more interesting is to look at the slope. So take the derivative first, 3x squared minus 12x, and then set it equal to 0 undefined. To find critical points, so this is how you would go about finding critical points. Factor it. X equals 0 and x equals 4. So these are critical points. Right? And then we do a line check with the derivative. Now I want you to label these line checks because we're going to be doing lots of different line checks. And you put these on here and you test a point. X equals 5. We're not doing true false, we're just doing positive, negative. So put 5 in here as positive, negative, positive. And then on what I usually do on these graphs is I draw a little generic arrow showing the slope, because these are slopes. And you can easily see now it's increasing, it's decreasing, it's increasing. You can also, these are critical points. You can also identify really quick that this is a relative max, and you can see the peak. And then you can see the relative min here, right? It's a peak, it's a valley. In fact, these are also stationary points, right? Because they came from 0 specifically. So there's a lot of information we get from here. But we could, if we were to write it, we could say that it's increasing on the interval negative infinity to 0, and we include the endpoints. We never include infinity, and it's also increasing on 4 to positive infinity. We could say it's decreasing on the interval 0 to 4, and you would include both endpoints. So that's how we could use line checks. Now, the other one is concavity, which is the second derivative. And so we take the derivative of the first derivative, not the factored version, but this one right here. It's going to be 6x minus 12. I'm going to set it equal to 0 undefined to find potential inflection points. So we could factor a 6 out. And x equals 2 is possibly an inflection point. The concavity has to change. In fact, I know it's going to change here because the only time it's not going to change, plus plus, it would be if it's plus plus minus minus, is if it had an even exponent on it, right? So, but we could do a line check to figure out where it's concave up and down. Test a number. It's positive, it's negative. So what I usually do on these graphs is I draw a little simple concave up or down symbol to match those sections. And then that also shows you this is an inflection point because the concavity changes, right? So you could say, okay, it's concave down on the interval negative infinity to 2. You never include the endpoints for concavity. Concave up on the interval 2 to positive infinity. You could say that there's an inflection point at x equals 2, right? So we can answer a lot of questions about that. Now, here's an interesting challenge. Could you sketch a picture of this curve? Like you have like all kinds of good information. Could you sketch this picture? Now, I'm going to do it right here. I'm kind of running out of room. But what we could do is we could say, well, we could start with the zeros. All right, x-intercepts are pretty important on a graph, right? And then you could say, okay, well, and then the graph is below, and above here. It's increasing over here, and then it's decreasing from 0 to 4, and then it's increasing from 4 onwards. But the graph does something like this. It's increasing, and then it's decreasing, and it bounces off the curve right there, and then it comes back up like this. So you have your x-intercept, your 0, that was a bounce, and it's also relative max is there at 0, and then you have relative min at 4. And it's concave down up until this point 2. There's an inflection point here. And then it's concave up the whole rest of the way. So we can kind of get a rough sketch of the graph from all this information. Okay, we do one with trig, just to throw it in there. We could just talk about the y values first if you want. G of x, I could set it equal to 0. Now, I don't think we're going to find the x-intercepts of this one very well. So, unless we had a calculator, or it was better, but this one, I don't think we're going to be able to solve for x. So we're going to skip that, the y values one. We're going to jump to the slope. So g prime of x equals 1 plus cosine of 2x. You got a chain rule here. You're going to multiply by the derivative of what's inside. And then we're going to set it equal to 0 undefined. And so we get cosine 2x equals negative 1/2. Reference angle. What is cosine equal 1/2? 1 root 3 over 2 root 2 over 2 1/2. 0 pi over 6 pi over 4 pi over 3. Quadrants 2 and 3 is where it's negative. So then we'll do 2x equals, quadrant 2 would be 2 pi over 3 plus 2 pi k. And quadrant 3 would be half circle pi plus alpha, so 4 pi over 3 plus 2 pi k. And then we would divide by 2, divide everything by 2. And so then we get x equals pi over 3 plus pi k, and x equals 2 pi over 3 plus pi k. This time it does matter that we look at the domain. So critical points are going to be pi over 3, 2 pi over 3, give these the least common denominator if you want. Okay, 4 pi over 3, and 5 pi over 3. So these are your critical points. And then we would do a line check. So g prime, so pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, and then the edges of 0 to 2 pi. Test a value, I'm going to say 0. It's my favorite for trig. Now you want to test this in the derivative. Make sure you don't test it back in the original function. People do that all the time. So cosine of 0 is 1 times 2 is 2 plus 1 is 3. So it's positive, negative, positive, negative, positive. It's going up, down, up, down, up. And it keeps going through these ends until it's the next root that we didn't find. So we could say, it's increasing here, it's decreasing here, increasing here, decreasing here, increasing here. This is a critical point, it's a stationary point, it's a relative max. This is a critical point, stationary point, relative min. This is a critical point, stationary point, relative max. This is a critical point, stationary point, relative min. So lots of good information from that. The second derivative, g double prime of x, would equal negative 2 sine 2x, chain rule, times 2, equals 0 undefined. So sine 2x equals 0. So alpha, or don't do alpha. Sine equals 0 at 0 plus pi k. So we're looking for x equals 0 plus pi over 2k. So x equals 0, pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and 2 pi. So these are possible inflection points. In fact, I know they are. I know it's going to change positive, negative, all these. We don't put dots for these, we just mark them. And we already have our endpoints are also points. So we can test a value, x equals pi over 4, or whatever, I don't know, pi over, we're going to plug these into sine, so I don't know, pi over 6 is nice. Sine of, well, yeah, I mean, whatever you want to do. You can do pi over 12 because it gets doubled, it's pi over 6, sine pi over 6 is 1/2. In fact, yeah. No, I'm going to do pi over 4 because then it's going to be pi over 2, which is 1. And no. Okay. Let's see. So pi over 2 is 1. So it's going to be negative. Negative, positive, negative, positive. And then it changes again over here. So it's concave down, up, down, up, up, down. So these are for sure inflection points. And you could, also identify what's concave down or concave up. So lots of good information from this. Anyways, we're going to do a lot of work like this, on our next test. I mean, some of it I'll just give you the pictures, but this is today's assignment. So all of these problems here are today's assignment. And all right, that's it. Try them out. Odds are in the back of the book. I might have the evens online for you to check. Try it out. And let's get familiar with all these terms and start to understand how to look for them.